In this video, we're going to take a look at a couple ways that we can interpret what a partial derivative really means. And again, we don't have to reinvent the wheel. We just have to reimagine what we know about derivatives from our previous work in calculus. So what do we know? Well, um, so let's say we have a function of one variable that is differentiable. Then we know, for instance, that so the two basic ways that we can interpret a derivative. So let's say we take f prime and evaluate it at a particular number. So f prime of x0, this represents the instantaneous rate of change. So the instantaneous rate of change, at x equals x0, right? And what does that really mean? Well, it gives us a way of measuring how quickly the function, our f of x, is either increasing or decreasing at that point, right? So that's what your f prime of x0, again, in a physical sense, right? It kind of, let me take this off instead of going too far to the right. This means it allows you to answer this question: at what rate is my function increasing or decreasing at that point, right? So at x equals x0, right? So that's the kind of physical thing, and that, that's why we end up using derivatives when we analyze things like motion, because motion has a lot of rates involved. The other way is more geometric. It's the slope of the tangent line to the graph of this function at x equals x0. So the slope of tangent line to y equals f of x at x equals x0, right? So we know the familiar picture. You have your graph. Again, as long as it's nice and smooth, right? So no sharp corners, at least where I want to have the tangent line, that is. And then let's say I want to have the tangent line right here. So then that would be my x0, and then the slope of that line is given by this number, right? And it turns out, for now, functions of two or more variables, we can imagine the partial derivatives, these first partial derivatives, as either rates or slopes, right? So let's start with the rate interpretation, right? So, and again, I'll illustrate these interpretations using functions of just two variables, but you can easily extend it to three or four. So if we have a function like this, right, and I'm assuming that our first partial derivatives exist at a particular point, right? So in other words, if I do my f sub x, and if I decide to plug in an ordered pair, we want to get a number out of it, right? So we don't want to get something that's undefined, right? So if we have this type of function, if I take my first partial with respect to x, and if I were to evaluate it at an ordered pair, right? Again, assuming this exists, then this gives me the instantaneous rate of change of this function with respect to x. So this is where y does not change, but only x is allowed to change. And if I then want to find at what rate is my z value increasing or decreasing, this is the thing that will give me. So let's say it like this. So at x0, y0, if y is held constant, so that's the additional thing, right? So if y is held constant and x allowed to vary, right, then this number, so this represents the rate of increase of z, or of, you could say, my surface. So this represents increase or decrease, right? Represents the rate of increase slash decrease of z, right? So if in my domain I start at this specific ordered pair, and if I were to change the x, so like increase the x value just a little bit, at what rate would the z value change? Would it change by a lot, or not by a lot, by at what rate would it change? Would it change at a small rate, a relatively larger rate? Well, that's what this partial derivative, this first partial derivative, can be interpreted as. And similarly, if I change that to a y, so if I have dz dy, and again evaluated at x0, y0, well, it's pretty much all of this. So I'm just going to use my wonderful copy and paste. So yeah, I can just take that, and like I said, why reinvent the wheel, right? We just, so all I have to do is switch the x and y here. So now in this case, my x is being held constant and y is allowed to vary. And then if I compute my partial derivative, and we now are getting used to at that particular process, and now evaluate it at a specific point, it's going to give me that instantaneous rate of change. And that instantaneous rate of change, whether it's positive or negative, will tell me if my dependent variable is increasing or decreasing, right? So that's good to hear, right? The way we've used derivatives in the past can be used again with this slight adaptation to say, okay, well, since we have all these different variables, but I'm really just differentiating with respect to one at any given time. So, right, we just envision it that, okay, all the other variables are held constant, and then the one that I'm differentiating with respect to, that's the one that's allowed to vary. This number is me that rate of change, all right? So it turns out that you can also interpret it geometrically. Now, these are a little bit harder because, yes, if we're looking at a function of two variables, then it means we're in 3 dimensions. We have our x or y as our independent variables, and then we have our z as our dependent variables. And again, those are just the standard ones. So let's say, let's start with our, and again, we're just going to use our first octant to illustrate this. And I'm going to draw a surface. Well, I'm going to try to. Wish me luck. So I'm going to draw, it's just a portion of it. So just think of it as a sheet that's floating above the XY plane. And let me just, kind of give the sense that, yeah, this thing, it's not necessarily a plane. It could be a plane, but it could be something that's curved, right? And then, so now I'm going to have a point here in my domain, right? So that would correspond to x0. That corresponds to y0. And then, of course, again, then if I were to take x0, y0, plug it into my f function, then I would get my z value here. So there is some corresponding point on the surface, right? So what happens when you take a partial derivative with respect to x? This is fixed, right? This y0 is fixed, but then this is allowed to vary just slightly. So what happens is when you change this, then the point on my surface will move. So for instance, if I slide x0 in the positive x direction, that's going to have an effect on where this point is, which means the z value will change. And then the question is, how does it change? So what we can do is, so it's not a curve anymore, it's a surface. So we can interpret, if we were to take the equation for the surface, differentiate it with respect to x, and then evaluate it at the point x0, y0, then that would give us the slope of the surface, but strictly in the x direction, right? So I'm not going to write too much on this, because then, my not so terrible, illustration will get all messy, and I kind of want to just look at it for a while. It looks, I'm impressed with myself. But so again, when we take the partial derivative of our function of two variables, evaluate it at a point, we can interpret it as the slope of the surface in that direction. So for instance, with respect to x, I'd be seeing how sloped is the surface in that direction. Is it so steep that it causes my z value to change dramatically, or is it relatively flat that there isn't a great change in the z value? And then similarly here, if I wanted to fix x and then change the y0, then I would be looking to see how the surface slopes in that direction, right? So in a nutshell, when we take a partial derivative, right, either with respect to y, x or y, we're actually finding the slope of the surface, but in a very specific direction. And it will be either a direction parallel to the x-axis or parallel to the y-axis, right? So let's write that down. So I think what's really nice about these two interpretations is that these are a direct carryover from our previous calculus work, right? Where you can either interpret it as a rate of change or a slope. So let me just write the symbol down. So dz dx evaluated at a specific point can be interpreted as the slope of the surface, right, at that point. So at x0, y0, but specifically in the x direction. So in the x direction, right? So again, if my change is a change that results where my point moves parallel to the x-axis, what does that how does that affect my z value, right? Then again, it can be interpreted like this. And then similarly, dz dy, the partial with respect to y, evaluated at that point, can be interpreted as the slope of the surface, right? Again, at that point, so at x0, y0, but now in the y direction. And there you go. So hopefully, I'm hopeful that you don't find that these two interpretations to be so far-fetched, right? That you're thinking, wow, what did I get myself into? But rather, you say, okay, yeah, I can see how it's just an extension of what I previously understood, all right? So let's just do a quick example, and I don't know, kind of sad, but I want to keep looking at my graph. But anyway, I'll keep it up there for as long as I can. Okay, so yeah, let's just look at a specific example here. And I'm going to take a really simple surface. So let f of xy be the surface, x squared over y cubed. So here's the question. So I wrote if. So is this function or the surface increasing or decreasing at, let's just pick a point, I don't know, like 2, 5, right? But I can't just leave it like that, right? Because then you don't know what direction it is. So in fact, let's do both. So let's do part A that says if we allow x to vary and hold y fixed. So, and hold y fixed, right? Or what if we decide to allow y to vary and hold x fixed, right? And not only that, not only can we answer these, but we can even say in which direction, x or y, would the rate of change be greatest, right? Or the magnitude of the rate of change, right? Or changes most rapidly, whether up or down, right? So you can say a lot just by computing these, right? So let's see what we end up with. So for part A, because we're now saying that we're allowing x to vary, but we're holding y fixed, so that implies a first partial derivative with respect to x. So we have to compute the partial derivative with respect to x for this one, and this is, pretty as simple as it gets, I mean, other than constants, right? But I would just interpret this as x squared times y to the negative 3. I would not even think about a quotient rule here, right? Don't overcomplicate it. So since we're differentiating with respect to x, we get to treat the y to the negative 3 as a constant. So again, let me just write down kind of symbolically, we're going to take the partial with respect to x of x squared, and we're treating y as a constant, so that constant multiple comes down. So we have the y to the negative 3. Now we get to do our power rule on our x squared, so we end up with 2x times y to the negative 3. If you have a distaste for negative exponents, we can write it like that, right? So this is in general. Again, you could just say generally what this function represents. It represents the instantaneous rate of change of this surface, but specifically in the x direction. And if we now plug in 2, 5, so take our partial derivative, evaluate it at 2, 5, then so that's 2 times the x value over the y value cubed. So this is 4 over 125. Now, as far as units, right? Again, I didn't give any units here, but this as a rate, right? Rates always have units. So technically this would be units of f, right? Or z if you wanted to use z, per unit of x, because it's only the x variable that's changing. So per unit of x. So it might be something like maybe, it could be meter per second, or let's say something like this, or maybe, pounds per centimeter, whatever this function might represent, and then whatever your unit of x would be, this here units of your function per unit of x would be the units for this partial derivative. Now, since it's positive, right? So since our df dx evaluated at 2, 5 is greater than 0, then we know the surface or the function or the z value is increasing at this point, right? In this direction, right? So f is increasing, right, in the x direction. All right, it's not a big rate. This is a pretty small number, but it's still positive, right? So increasing. And let's look at b. So b, now we take the partial with respect to y. So remember, our function was x squared over y cubed. Now, I can pretty much see it here. The only difference now is that x squared is going to be treated as a constant, so that will come down. And then I have to do the partial with respect to y of my y to the negative 3, right? So still the power rule. And now, so this ends up being x squared times negative 3y to the negative 4, right? And then we end up, so that's it. So then let me write this. So we have negative, I'll write the 3x squared like that, and then in the denominator we'll have y to the 4th, right? And I think you see what's going to happen, right? When we plug in, so if we take our partial with respect to y and evaluate it at 2, 5, we have that negative there, and then we'll have 3 times the x value squared over the y value to the 4th power. So this is, what do we have here? So it's negative, that's 4, so negative 12 over 5 to the 4th, that's 625. And in this case, it would be units of f per unit of y. But again, it's really interesting just changing the direction. So instead of changing the point in my domain, so you're at the point 2, 5. If you move in a direction in the positive x direction, your function will increase at this rate. If you move, again, starting from the same exact point, if you now move in a direction towards the positive y, then your function will decrease at this rate, right? So the direction does significantly affect what happens to your dependent variable. So to answer the question, we will say, since our partial derivative with respect to y evaluated at that specific point is now negative, our function or surface, so f or z, is decreasing in the y direction, right? Or another way you could say it, you could say that the surface is sloping upward in the x direction, but it's sloping downward in the y direction. Again, that might seem a little strange. It's like, how could you do that? Starting at the same point, how could the same surface exhibit that type of behavior? Well, it's because of how it's curved. It's the curvature of the surface that's affecting this. It might be relatively flat or upwards in one direction, but then in another direction, it might be downwards. Think of, walking on, like a hilly terrain. Depending on where you go, you might be going up a hill or down a hill or, something like that. So that's the interesting thing about these surfaces. And it just takes a little while for you to kind of get out of the mindset of, okay, just a curve that's either going up or down at a specific point, or maybe constant, right? You have to now allow for changes in this third direction, right? All the fascinating things that happens in 3 space. So hopefully you found that interesting, and we're going to continue working on these derivatives. And to do so, I'm going to hop on over to the next video. Why don't you join me? See you then.